Hello everyone, my name is Madhvi and in this video tutorial, we'll together embark on a journey to understand QUIC from its core concepts to its practical applications. After TCP dominating the transport layer world, QUIC is the next protocol which has been recently introduced for running the transport layer services. It is a protocol that has already been running many web applications by now, including YouTube, Facebook, and even some mobile apps such as Ola and Uber. We will be discussing about this in the later part of this video. Now, let's begin by discussing what QUIC actually is. QUIC, also addressed as QUIC, stands for Quick UDP Internet Connection, and it's a transport layer protocol newly developed by Google that aims to improve upon TCP's performance by reducing latency and providing better congestion control mechanisms. It operates over UDP for faster data transfer and incorporates features of both TCP and TLS to provide a secure, reliable, and efficient data transfer. Also, it uses HTTP/3 as its application layer protocol, which helps in improved performance even when the network conditions are weak, thus having a better resilience to packet loss. Moving on, let's discuss about the need for QUIC. Traditional protocols like TCP and UDP have served us well, but they come with some limitations, one of which is head-of-line blocking, where a single lost packet delays the entire data stream. QUIC emerges as a solution to address these shortcomings, offering reduced latency, improved performance, and enhanced security. It uses multiplexing, allowing concurrent transmission of independent data streams within a single connection, and it streamlines the connection setup process, thus reducing the round-trip time. Time taken by TCP handshakes are also a limitation. However, when considering QUIC handshake, it combines the elements of the traditional TCP handshake and TLS handshake, aiming for efficiency and security. As it works over UDP, we no longer need to waste a lot of time on handshakes, and after just sharing a hello and finished messages, direct exchange of data takes place. Apart from this, congestion control and increased latency are some of the challenges posed by TCP. Its reactive approach relies on detecting packet loss to adjust transmission rates, leading to latency spikes in congested networks. In contrast, QUIC addresses these issues by considering additional factors beyond packet loss, enabling more efficient responses to network congestion. Moreover, it leverages error correction techniques to reconstruct lost packets without retransmission, reducing latency and enhancing efficiency of data delivery as compared to TCP. These innovations allow QUIC to overcome TCP's limitations, providing users with a more responsive and reliable communication experience. Moving further, let me walk you through the motivations behind the development of QUIC. Its frame formats play a crucial role in facilitating efficient communication. Let's explore them in detail by analyzing it over Wireshark to grasp its inner workings. So here, while analyzing QUIC on Wireshark, if we look into the packets captured here, we can see that QUIC first sends an initial packet which has a larger packet length. This is different than TCP because the length of a TCP handshake is always very small and it sends very small packets. On analyzing this packet, we can see that it uses UDP and works on the destination port number 443. Now looking more into it, we can see that we have QUIC IETF, and the version being used here is version 1, which is the standard version of QUIC, which is used nowadays. Earlier, it used draft 29 version, which was actually a somewhat stable version that the protocol before of that protocol before version 1 standard came. And if we look into its encryption here in the crypto part, we can see this that we have the TLS 1.3 handshake in the initial packet itself. So we are sending a client hello here over the server. So here is the client hello. So now I would like to show the server here that is being requested. Here we can see the server name, which is google.com. Also above here we can see in the ALPN protocol, we can see the H3 protocol, that is the application layer protocol, which represents HTTP3. Apart from that, if we see in the quick transport parameters, here we can see all these parameters that are actually similar to the TCP options, and these define the two endpoints that can communicate to each other. At the end, if we look at the padding, as told earlier, the initial packet is actually very large in size, and padding is what makes it larger. Before moving on to the next packet, the last thing we need to see here is the quick connection information, which is actually the header containing the destination connection ID and the source connection ID. These IDs are really important. Each endpoint selects the connection ID for the opposite side, which uniquely identifies this QUIC connection. Now this connection can actually live on even if the underlying protocols change in some way. Like if we take an example that while watching a video over your Wi-Fi, if due to some reason you need to move out of the range of the Wi-Fi and you switch the network, then in that case your IP addresses would change and maybe the port numbers can change, but the quick connection will still stay the same, and it just migrates into a new configuration. So that is one of the advantages of QUIC, that it can seamlessly migrate even if the underlying protocols change. Now let's move on and analyze the initial packet that is being sent by the server. This is the packet, and here it can be seen that this is the source connection ID, and the destination connection ID is actually 0 here. Below this we can see the length of this packet, and if we come down to acknowledgement here, so this is actually where we acknowledge the packet that was sent by the client to the server. This is how the server is acknowledging that packet, and this makes QUIC even more reliable because it acknowledges the packets in the same way that TCP acknowledges the sequence numbers. QUIC acknowledges the packets. Further, if we come down, we can see the server hello here, which is supported again by the TLS 1.3 version. The server is now responding to the client through the server hello, and below this we can see the cipher suite and the supported version of TLS. Now, as we do not have the decryption key here, so we can analyze up to this point only. But in the next packet, we can see that the acknowledgement packet from the server, from the client, showing that it received the server hello, is what is represented by this packet. Also, here we can see the packet numbers that are being shared. This is packet 1 from the client, and this one is the packet 1 that is being sent by the server. Further, this is the packet 2 that is sent by the client, and so on. Moving on, we have the handshake that is done here. This complete part that was done in the initial packet was the handshake part, and below that the encrypted conversation begins. The payload here is the short header. Like if we analyze this packet, we have a short header over here, just this much. Also, here we can see that QUIC protocol does not support fragmentation, so it cannot be fragmented, and we do not have any fragment numbers over here. So that was all for the analysis of QUIC using Wireshark, showing all the frames that are being used in it. Further, QUIC offers several significant advantages over traditional transport layer protocols like TCP. One of its primary strengths lies in its ability to reduce latency by reducing the time taken by three-way handshake as required by TCP. With QUIC's innovative Zero RTT feature, handshakes are lowered, resulting in faster connection establishment, particularly beneficial for real-time applications like online gaming, video conferencing, and live streaming. Furthermore, it provides enhanced security by integrating encryption and authentication by default, mitigating the risks associated with eavesdropping and tampering, making it a more secure option compared to TCP. Its support for multiplexed streams allows for concurrent data transfer over a single connection, reducing head-of-line blocking as explained earlier, and further optimizing the performance. Moreover, QUIC's seamless connection migration capabilities enable the users to maintain connectivity across different network interfaces without interrupting ongoing sessions, enhancing reliability and scalability. These combined advantages make QUIC a compelling choice for modern internet communication, offering improved performance, security, and flexibility for a wide range of applications and use cases. Apart from the benefits it offers, QUIC also presents several limitations and challenges that need to be considered. Firstly, it introduces additional complexity compared to TCP, both in terms of protocol design and implementation. This increased complexity can make it more challenging to deploy and maintain, particularly for network administrators and developers who may not be familiar with the protocol. Additionally, its use of UDP instead of TCP may pose compatibility issues with certain network equipment such as firewalls and proxies. These devices may not fully support QUIC or may require modifications to adapt its unique characteristics, potentially complicating the deployment process. Lastly, QUIC is still relatively new and not yet universally supported across all platforms and browsers, leading to limited deployment. Its restricted deployment may hinder this widespread adoption and necessitate fallback mechanisms to support protocols like TCP in certain scenarios. It's important to be noted that QUIC isn't just a theoretical concept, but it's powering some of the most popular web services and applications today, showcasing its real-world impact and potential. For instance, major players like Google, Facebook, and Cloudflare have adopted QUIC to optimize content delivery and enhance user experiences on their platforms. By implementing QUIC, these companies have witnessed significant improvements in performance, particularly in terms of reduced latency and faster page load times. Users benefit from quick access to web resources, seamless streaming experiences, and overall enhanced browsing performance. Additionally, QUIC's scalability is a key feature, allowing it to adapt seamlessly to various network conditions and accommodate different levels of traffic. Its ability to adjust to changing network landscapes and dynamic traffic loads is central to its scalability. For example, features like connection migration enable QUIC sessions to transition smoothly between different network interfaces, such as switching from Wi-Fi to cellular data and vice versa. This ensures uninterrupted connectivity and smooth user experiences, especially in environments with fluctuating network conditions like mobile networks. That's all for my tutorial video. Thank you for watching.